Howdy everybody, welcome back to Professor Carbon. In this video, what we're going to do is just go over some very quick reactions that amines and ketones and related functional groups can undergo. And so let's just get started by looking at our first reaction here. And so hopefully we can all recognize that benzyl bromide is a really great electrophile for substitution chemistry. And in this case, we have trimethylamine as our nucleophile. And hopefully we recall that when you have really great electrophiles, you can actually undergo this substitution reaction and quaternize that nitrogen. And so in this particular case, our end product is actually going to be a salt. And so it's one of the few reactions where we actually end up making a salt at the end of the day. It turns out that molecules similar to this are actually used as disinfectants in some products. So if you have a home humidifier and you have the little can of disinfectant that you put in your humidifier, go ahead and look at the back of that label, and it'll probably have some ammonium bromide salts. And those would be things similar to this. All right, let's look at the next reaction here. This one is a tri-component reaction. So we have formaldehyde, we have dimethylamine, and we have acetone. And so there's got to be a lot going on here if we need all three of these components. So the first thing that hopefully you can recognize is that dimethylamine and formaldehyde can come together to make an ammonium salt. And in this particular case, it's going to be an aminium ion. And typically water is going to be the corresponding negative charge. So it might have some hydroxide around, or we might be promoting it with something like sodium acetate or acetic acid, and the acetate might be the counter ion as well. But regardless, this is going to be a really great way to make an aminium ion, and the aminium ion from formaldehyde and dimethylamine is going to be quite electrophilic, and so it'll end up being attacked by the enol form of acetone. And so I'm just going to put an equilibrium arrow there so that we all remember that ketones and enols are in equilibrium with each other. The enol is going to be just nucleophilic enough to engage that aminium ion. And so depending on the conditions, we could get a variety of products. In this particular case, I'm going to draw the adduct. Okay, and the next one here, we now, let's look at both C and D together, because our instructions for D are that it must be different than C. And all we have to do now is come up with some conditions to convert that bromide to a nitrogen. And I think the conditions that most people might want to try first is to have ammonia just be the nucleophile and do an SN2 reaction, just like we did up top here. The only issue with this is that, remember, you'll have over-alkylation. And so if we just use ammonia, we'll end up with a variety of products. That could be benzylamine. It could be dibenzylamine, where we have two groups coming on off. And we could end up with tribenzylamine. And we could also quaternize, just like we did in the top example. And so to avoid that, there's a couple of classic workarounds. The one that you can consider probably first would be to use sodium azide. And so that'll be a very good nucleophile. Azide is a fantastic nucleophile, and so we'll make the benzylic azide. The nice thing about the azide anion is it's really only nucleophilic once, and so there's no risk of oversubstitution. And the azide group reduces down quite nicely with one of our favorite sets of reducing conditions. In this case, palladium on carbon with some hydrogen gas will easily reduce that azide to a combination of nitrogen gas and the amine. And so that is one of the kind of two classic ways to avoid this issue of overalkylation. The other of which is to use the Gabriel synthesis and use an N-phthalimide. So I'm just going to draw that out now over here. And so you can use sodium or potassium phthalimide. I believe the potassium salt is commercially available from Aldrich Chemical or a wide variety of other vendors. And so it's pretty stable. The nice thing about phthalimide is because this negative charge on nitrogen is delocalized into not one, but two oxygen atoms via resonance. It has a pretty low pKa and it's not particularly basic. And so because of that, you can do this chemistry in water without really worrying about accidentally protonating your N anion. And for really good electrophiles like benzyl bromide, it'll alkylate without a whole heck of a lot of problem. And so that's kind of nice. And then the classic conditions to remove the phthalimide group are going to be hydrazine. Now, a little bit of a safety note for you, both azide, which is used up here, and the hydrazine down here are known to be hazardous materials. And so before actually using these chemicals in the lab, I would encourage you to consult somebody who has experience working with them and to carefully go over a safety protocol to make sure that you're not risking any hazards. All right, last two couple of reactions here. We're going to go away from amines and just look at some reactions of esters and carbonyls. Now, this particular one, we have to identify the starting material in E, and there's a little bit of a hiccup there, and that is the conditions are kind of vague. So they're just acid, water, and heat, and there's not a whole lot of an idea of where that could be coming from, because this looks all in all like a pretty kind of generic ketone. And so what I would notice though is that we have a tertiary center next to that ketone, and hopefully we can remember that acids beta to ketones can undergo a decarboxylation reaction. And so I think the key clue here is going to be heat, where we actually trigger that sigmatropic elimination of carbon dioxide. And so let's just draw out a starting material that has a carboxylic acid in it. Like so. And then that might be a really good piece to alkylate. And so for those of you that may recall, it's a lot easier to put these alkyl groups in place when you have a beta keto ester than it is with a regular old ketone, because that ester really lowers the pKa of that site, and it makes it acidic enough where you can do that chemistry in something like water or alcohol solvents, which is a real attribute over something like lithium diisopropylamide. And so it's a very nice classic trick to avoid very strong bases in anhydrous conditions. All right, the last one here is another good classic reaction. So sodium ethoxide is going to deprotonate over here. So let's just draw that out. So that'll end up making our enolate of cyclohexanone. And then this is going to attack and do an acyl substitution in 2 steps from ethyl acetate. And so we should end up with the beta keto ester. And I'm drawing this in the neutral form. Some of you may recall or might be curious about if we actually have the anionic form before our workup, and certainly that would be the case. But I'm going to draw it after the workup step. Okay, so hopefully that was a great review of a number of reactions that ketones, esters, and amines can undergo. And again, thank you for tuning into Professor Carbon. Please subscribe to the YouTube channel and please view another video. It's been a real treat to be able to put all these together.